Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a pleasure to have with us Ricardo Silva from UCL. And Ricardo basically works on machine learning, and one of his important sort of research direction is causality, which we were sort of talking about, and Bayesian inference. So over to Ricardo.
Okay, thank you. Can you hear me well? Okay. First, thanks for inviting me to give this talk. Not really going to talk about causality today, but towards more the general area of probabilistic modeling within the context of machine learning. So to give you a general idea what this talk is about, I'm going to use this running example, which is a big survey applied to NHS in 2009. It's basically about staff satisfaction. So the staff members of NHS had to answer about 150 questions, I think, on a variety of different indicators of satisfaction of their job. Here, for example, we have a section on your relationship to your immediate manager. So there are different items there trying to measure how well your relationship with your immediate manager is in different aspects, like whether the manager provides feedback to you, whether you think the manager is reliable to rely on and you have some need, and so on and so forth. These questions, most of them are given this so-called Likert scale, where you have some ordinal encoding on how well you agree or disagree with these particular statements that you find in each section. So this is basically the structure of the data they collected. Here they had about 150,000 staff members answering this question. And as you can imagine, this is actually quite a lot of work to answer such a long questionnaire. And might think on what other kinds of uses they make out of this data, and how useful it is to measure such concepts with so much precision if the cost of that is actually taking some staff time, for example. So what uses people make out of this data? Here I'm going to focus on just one use, and this is going to be the stepping stone for the methods I'm going to introduce. So it's not uncommon to have some sort of postulated latent traits of interest in a population. These latent traits sometimes are very hard to define. So if you're a political scientist, for instance, you might be interested in ranking nations according to their levels of industrialization and democratization. These are kind of abstract concepts, but somehow you'd like to measure that in one way or another. And that's how some people come up with indicators such as gross national product or some expert assessment of democratization by asking experts to rate a country on how free the elections are. This is just a simple example. So some people have to fill in these answers to these questions to measure traits of interest. And then what happens is you might be interested in the embedding of your objects in this latent space. So here in the right-hand side picture that I'm plotting the data in this latent dimension. So here I have about 75 countries, and I have their conditional distribution of these latent factors given observations that come from a questionnaire. And the distribution is over some real space. So what I have here I have the sample space for the democratization level. And here I have some box plot capturing, I think, 95% of the mass of the distribution. And I have a longitudinal study, so I have actually this at over 2 time points. And this is a plot that is organized sorting the countries by the expected value of their industrialization. So this gives them a kind of summary of these traits where interested in the latent distribution given the observations. So one interesting thing here is about designing measurements that measure these traits such that what you have there is useful for scientists in that domain. So here you might want to compare, for example, trends over democratization distributions as you vary industrialization factor as a summary on how the two concepts are associated in the population. So in one way, what is happening is that all the information that you are based your conclusions on come from the condition distribution of these latent variables given the observations. Okay? So here my assumption would be all the information that I'm interested in here, in this domain, is postulated to be contained the condition distribution of the latent variables. So given this is my working assumption on how we're going to use these models, what I'm going to do is to develop some methods by which you can design better ways of measuring these latent traits. So I'm going to go through two main topics here in this talk. One of them refers to what I call model compression. If you're going to have some sort of long questionnaire to capture information about latent traits, it might be useful to you to design short questionnaires for reasons I'm going to explain soon enough. In terms of machine learning context, of course, is related to something that we know is active learning, but in a slightly indirect way, as you're going to see. The second main topic is about really on learning itself. So you might have some background knowledge on how these traits should be measured, but the background knowledge might be imperfect, and how can you extend an explorer-driven model with some adaptive method to better capture the distribution of the latent variables. So this is the second part, and is related to the ideas that you find in graphical model literature on structured learning. The methodology for solving this text will be based on some very well-known building blocks, such as graphical models, combinatorial optimization, and approximate inference. Okay? So feel free to interrupt me at any point. I'm not sure exactly how far I'll be able to go in the talk. Maybe I won't have enough time to cover everything, but I plan to. But it doesn't matter. You can interrupt me at any point. I appreciate it. So the first topic on model compression, sometimes this is known as, in social science literature, in psychometrics literature, as how to shorten scales, how to shorten sets of measurements that you design in order to measure some latent trait. It's the point of view of somebody who actually answers some questionnaires. I like to call this a method to minimize the annoyance of whoever has to actually reply to these questionnaires. So how does it work? What's the motivation behind this? So you might have a long questionnaire to reply to, but it doesn't mean that it's of the interest of the scientists or whatever organizations collected that data, that the questionnaire is as detailed as possible. The reason for that, of course, humans have to reply to these, and there is pay some sort of cost that they have to pay to actually fill in this data. So if you have a very large set of questions, your refusal rates might be high. Some people might just say, okay, I'm not going to reply to that. Please don't bother me again. Or you might have people who agree on replying to that, and after a while, they might get tired. The answers are not given with as much confidence as if they had a fresh start. It might induce some dependence between your patterns of answers because of that. And this might bias your results in some undesirable ways. So you might as well, instead of having data of lower quality, try to focus on some more important measurements, those that carry most of the information. So we assume here that we have a given model to measure some latent traits, but this model can be simplified without much of a loss of information. Okay? So there will be no learning step in this case, no estimation. I'm assuming that you're giving a model and I wanted to reduce the amount of effort that takes me to provide the observations that will be fed in this model. Okay? So how is this going to be formulated? I'm pretty sure there will be at least a few people in the audience that will think exactly the same way, because this is a very standard way of expressing how you can summarize information. So I'm going to call here X my set of latent variables, traits like my example, industrialization, democratization. I'm going to call y my observations, would be in this context answers to a questionnaire. So I'll be interested in selecting a subset of y to preserve as much information in the conditional distribution of x as possible. So one way of measuring that is by a divergence measure between these two conditional distributions, an average over the distribution of your data. And one common measure of divergence is just the KL divergence. Okay? So you have a KL divergence between the conditional distribution given every possible observation and one conditional distribution giving a subset of your observations. Your decision variables here, this problem is your set Z that you have to pick out of a collection of questions. And here, you have to be provided some sort of size for this set. So you say, I want exactly k questions to be preserved such that this distribution is close to that. And I will not be concerned here on the size of k, how this is chosen. This is a trade-off parameter, and here I'm assuming it's given to you by whoever is interested in this study. Yes?
Two questions. The first is it actually a reasonable assumption that this model is known a priori? I mean, I have no idea about questionnaire design, but it would seem to me that in many cases one perhaps comes up with a set of questions that one finds reasonable, and then later on one does some explorative analysis and tries to find some sort of latent traits or latent variables that could explain those answers, so you don't have this model a priori.
Yeah, you're right about that. So there are different ways by which people converge to some sort of latent variable or some sort of model over the patterns of answers. So yes, you can think of a completely adaptive method that people start from the measurements and try to see which are the common explanations for the associations. Or you can think in other scenarios where people design their questions to measure traits of interest. Here, I'm just assuming that you have your latent traits that are your target traits. How you obtain this I'm being indifferent to that. But you do have your traits of interest. Okay?
The second question was, does it make sense to constrain yourself to a subset? Or might you be interested in sort of just asking different questions, and then you'd be able to ask fewer questions, not necessarily a strict subset of the questions in your original set Y.
Right. I mean, the actual design, what you're going to measure is a much more complicated, much more domain-oriented task. Here, I'm focusing on subset first because it's much simpler. But you, of course, just changing the nature of the question is another way by which you can simplify your set, right? You might say, I'm substituting one set by a smaller set of a different type. It's just a much harder to define problem than this problem that starts already with some work that was done before. So how can you tap in this previous work to get a simplified questionnaire? Okay, good. Right, so this is a general goal, optimizing over subsets. I can rewrite that KL divergence in terms of a more direct cost function with explicit binary indicators encoding whether a question is included or not. So ZIs are indicators whether the question I is included or not. And here I'm assuming that observations Y are conditionally independent given X. So given the latent variables, they factorize. And this allows me to write down that KL divergence in this as this function, where you have a linear combination of these log conditional probabilities, and you have an entropy term. An entropy term over the distribution of the observables in the set of your choice. Okay? So here, this is basically integer programming formulation under this constraint that you have a choice of exactly k questions. All right? And at this point, it's a very complex nonlinear integer programming because of this entropy term there. So we can actually see that this is equivalent to minimize the conditional entropy of the latent variables giving a set of your choice. And in some situations, this is known to have some nice combinatorial properties. This situation that I have here where my observations are actually independent, given the latent variables, you can show that as a function of your set, your choice of variables to keep, this is a submodular function. I'm not going to get into detail here, but basically this entails that there's some nice properties you can exploit while optimizing for the choice of Z. Okay? But one difficulty here, even under this scenario, is that the objective function is not easy to calculate. Sometimes people do these combinatorial searches where this entropy term is easy to calculate. This Gaussian, for example, the joint distribution, then you can calculate easily what the entropy of the joint Gauss would be. In this case here, I'm assuming you have discrete variables. And later on, I'm going to assume they're actually binary for simplicity. And in this situation, you cannot even calculate your objective function because it depends on this entropy term. So the main goal here is the first part of the talk, is to develop some procedure which tries to solve this hard combinatorial optimization problem. At the same time, it's trying to approximate this objective function. And to that, to some extent, where the optimization between the set you're going to pick is intertwined with the approximation to the objective function. Right? So to make things more concrete, I'm focusing on a particular model, which is one of the most common models used in this situation, which is a multivariate probit model. So assuming your latent values are jointly Gaussian, and without any loss of generality, you can make them zero mean. And you can imagine having binary observations which come from truncating some intermediate Gaussian that is generated from X. So you have this intermediate Gaussian variable which comes from a normal distribution condition on X. I mean, again, without loss of generality, you can assume its variance is 1. So if this is greater than 0, your outcome is 1. If it's less than 0, outcome is 0. Okay? So for simplicity, focusing here on binary answers just because it's going to make some calculations simpler. But this is not essential. What is interesting about this problem is that you can calculate some small margins without much effort. So you can calculate the marginal distributions of the y's easily without any Monte Carlo method, just a simple quadrature will make it. And you can calculate small dimensional marginals easily too, by all sorts of methods. So you can calculate joint distributions over y's for small sets of y's in some relatively simple way. So this is a property that is going to be important when designing my procedures. Okay? So what would be one way of trying to solve this problem, tackling this difficult optimization problem? One of the simplest ways is just pretend your data is Gaussian. And then just plug in the Gaussian approximation for that, which in this case, the entropy would reduce the log determinant. Okay? And calculating the log determinant is, of course, tractable. I'm assuming you don't have that many questions here, so you can calculate this without much effort. And this gives you a tractable objective function. Then you can throw at it any of your favorite combinatorial optimization methods. So for example, doing the greedy approach that is often used in submodel optimization, you can apply that here. You can calculate this covariance matrix easily from this model. I don't need really to have something like an EP for this simple model because you do have the marginal distribution of pairs of variables easily. So you can calculate them, the covariance independently and put them together in a covariance matrix. You're done. Go on. So this would be the simplest thing to do. Yes?
So in the greedy optimization, in the exact case, you get a 1 plus 1 by e approximation in the submodular function case when you were finding the best guy in each iteration. In this case, you are using an approximate sort of algorithm to do the greedy step. So, but are there any bounds on the accuracy of this step? And if yes, do they propagate over to the final sort of bound that you get on the overall set solution?
Well, I'm not sure about that, to be honest. Okay. Okay, so of course, if you want, try to estimate this by Monte Carlo, which of course is going to be very difficult in general. Actually, you can't do Monte Carlo to the MCMC because I'm going to condition some of the observations, so you cannot do exact Monte Carlo there. I have to do MCMC. So and then the Gaussian approximation is just one of the first things you could try because it's cheap, and you can just use the tools of the trade there without any modification. So I'm looking here at some alternatives to that. How you can approximate this entropy in a way that's also related to your choice of Z. So one way of doing this is looking at this very simple relationship of entropy, that if you condition a larger set, your entropy can only go down. It never increase as you increase your observation. So with that, you can build a very simple bound by, for example, choosing a particular order for your variables. And in this order, you can decompose the joint entropy as a sum of these conditional entropies, where every element in this order is conditioned everybody preceding it. Okay? Then you can just bound this quantity by using a subset here instead of the whole preceding set of variables. This gives you a very trivial upper bound on the joint entropy. So what's the free parameter? Here's the ordering that you have. So you can try to get tighter bounds by picking different orders so that this is minimized. Okay? And there are all sorts of methods for that, some of them coming just from the literature on learning Bayesian networks, where essentially if you have a directed acyclic graph, the most difficult step here is picking the right order to factorize your distribution. There are all sorts of methods you could use at this step, including some very simple greedy approaches. So here I'm assuming that I'm given a neighborhood size, depending on your computing capabilities, to choose how large your neighborhood can be. And based on that, you're going to choose the order and choose your neighbors within the condition that they should precede you and be of a particular size. Okay? So here I'm just using standard tools for Bayesian network learning. You can approximate that entropy by optimization of orderings and bounded sets. So nothing here is making use of my choice of variables. So this is just a general optimization procedure to get a joint entropy and reduce that to a sum of small entropy terms. Okay? Now, what do you do with this? Okay, once I have this order and I have my choice of neighborhood, I'm going to plug this into my objective function here as a substitute for the joint entropy. So what you have there is an upper bound in the original objective function. Here, you can encode the original joint entropy in terms of your indicator functions of which values are going to be selected. So you have this term that goes over the order, and what this term means is the entropy that is given by the intersection of the variables that are in my neighborhood and the variables which are actually selected. Okay? So I'm only including here as my preceding conditioning set those which are selected. Now, of course, if my variable here has not been selected, this whole term is dropped out of the sum. So these variables here mean they are functions of the original indicators, which basically are defined in terms of product of which variables are actually included in Z. So regardless of what the subset of the neighbors that I have here are picked by my selection, I can indicate this function in terms of a product over these original indicator functions for every possible subset of my neighbors. So if I have a subset of size 5 here, I have exponentially many, I have the power set of it to the power 5 possible combinations that will be picked in my objective function depending on what my Z is. Okay? So of course, this is exponentially the size of your set, but you're assuming that you're choosing the size of this set according to your computational capabilities. So I'm assuming here this is tractable in the size of your problem. So for any configuration of Z, I have a corresponding combination here that gives me the right entropy term, depending on which ones are actually used. And here, this particular step can be, again, rewritten as a set of binary variables. Because basically this is saying, look at every possible subset of this, return the entropy term that corresponds to those in Z. And this means a product over indicators of the elements of Z. So it's again a binary variable. Okay? So for each choice S here, I can have one big binary indicator saying this is the term that corresponds to that set. And this big, horrible binary indicator can be written in terms of linear constraints with respect to the original variables. So just to give you one example, let's say that this set here is this set corresponds to variable 1, 2, and 3, for example. And this set is going to be picked only if the Z for variables 1, 2, and 3 is 1. Okay? So there is a relationship between saying the set of 3 variables is picked and every element corresponding to this set has this Z equals to 1. And you can rewrite this as a linear inequality constraint, which I'm not going to get into detail here. But basically, this combination can be written as a function of Z with a linear inequality constraint, which means this whole objective function here can be written in terms of binary variables with linear constraints. And this is going to be linear in these binary variables. Yes?
So the neighborhood is fixed, right?
The size of the neighborhood, yeah, I mean, the candidate set for the neighborhood is fixed in advance, yes.
But you can optimize over it, right? You can basically find out the tightest bound in some sense. So that would sort of relate to a max-min problem, right? You're maximizing the overall objective, minimizing over the neighborhood set.
Mm-hmm.
So yeah, okay, but that is you have not done that.
Well, I fix in advance what the ordering and the sets are going to be.
I see.
Okay, and this is my approximation of the entropy. It's just plugged in there. And this, of course, has consequences, which I try to explain here. So if you have the original model, of course, is a fully connected model because when you marginalize the latent variables, you induce dependence between all variables. So you can imagine its distribution being called as some sort of DAG factorization, directly signigraphic factorization. And the entropy is just the sum of these conditional entropies. And you can approximate this by restricting the sets which are conditionally on. Okay, so here, for example, I try to approximate the distribution with a distribution that has a sparse structure, okay, where I can calculate the entropy of this. But when I combine these two together in my variable selection problem, there are some artifacts that are undesirable there. So for instance, suppose I have only 3 variables, and the approximation that is chosen by the order search and the neighborhood search corresponds to this Markov chain here. Okay? So this will be the approximation that results from having the whole joint distribution. Now, when I'm searching for subsets, I'm searching for subsets of that. Okay? So suppose I'm choosing 2 out of these 3 variables using this approximation. So if I were to choose variable 1 and 3, for example, they would correspond to, and in reality, if I'm using this approximation, what I should use is the joint entropy or the marginal distribution of y1 and y3 together. So ideally, this would correspond to using my objective function, the joint entropy of this model, because this model is the marginal distribution of that model. Okay, if I marginalize y2, my approximation entail this should be the structure between y1 and y3. But in my simplified setup, what I'm doing is since y2 is not being selected, I'm just using this subset of my neighbors that does include y2, which in this case is the empty set. So when I'm choosing my z to be variable 1 and variable 3, I'm using the joint entropy of this DAG model instead of joint entropy of that marginalized DAG model. Okay? So this is a simplification in order to preserve an integer linear programming problem when you're doing the variable selection, to avoid intertwining between calculating marginal distributions over DAGs, which is itself intractable. So I cannot calculate marginal distributions directly in any case. So this is a simplification of that. Okay? So this says some undesirable properties, of course, because this is even a looser approximation than what I would get if I could marginalize my original approximation. So in a situation like that, which alternatives do you have? Well, if it's hard to marginalize a DAG in general, maybe you should look for simpler even simpler structures than this, which you can marginalize efficiently within your objective function. Okay? So the next step is looking to a variation of this idea where your bound is more adaptive to your choice of Z. So one different user of this entropy bound is looking here at all sets of size 1. And you can, of course, get the tightest bound here by just looking at every possible candidate and picking the one which gives you the tightest bound. Right? So instead of looking at neighborhoods of a particular size, you look at those of size 1. The difference here is the minimization problem. Instead of being predefined and fixed before I build my integer linear programming problem, this is now going to be used within the objective function. So I'm carrying this now within my variable selection combinatorial search. So here, my combinatorial search will include this main term instead of having the neighborhood being prefixed. And again, without getting much detail, I can rewrite this function in terms of a linear function of binary variables. Okay? So my choice of neighborhood is now part of the objective function, and I can have a tighter search within this family because it's not prefixed before I choose Z. Okay? So how does this translate in terms of approximating models? So suppose I had 4 variables. Again, the numbers here indicate the actual order, but it is chosen by the order search procedure. Again, the order, that's still prefixed. But within this order, the choice of neighborhood changes with Z. So in my left diagram there, I have the original complete distribution where I would select all variables. And now I can imagine a rearrangement of this tree structure when I select only a subset. So if I have a subset which drops one of the variables, and this variable happens to be Y3, for instance, my objective function is going to be related to another tree structure instead of just dropping on this edge. And this other tree structure will just link Y4 to some other predecessor, depending on the strength of the association that. So when you choose your Z, your tree structure here includes new dependencies that didn't exist directly in the original joint formulation. Okay? So it's one step further than the previous attempt in the sense that this structure depends on Z now. Okay? So these are the 2 main methods. I'm just going to compare this against some other alternatives. One very simple alternative that doesn't use any entropy term consists in using the so-called reliability score, which is defined for Gaussian distributions. But I'm going to use these reliability scores here as if my data was Gaussian. So basically, it's the amount of variance that is explained by the latent values for each one of your observations, okay, if your observation was Gaussian. Then I have this linear program here that just maximizes the sum of the reliability scores over my choice of subsets. So this would be a very simple comparison model approach to compare to, which doesn't require any entropy term. Of course, by not having an entropy term, it has some bad artifacts, such as it could choose for a single latent variable only indicators of it, because these are indicators of very high precision, So we never had to choose an indicator for another latent variable, for example, if this is the case, because you don't give any incentive for diversity there. Okay. So evaluation will consist on comparing different methods on how well they can reconstruct latent posterior expectations with respect to using all observations Y. Okay. So I'm going to just quickly explain. I did some synthetic study first with two different scenarios. One where there is a higher signal-to-ratio noise in a measurement model, with one with a smaller signal-to-ratio noise. The details are in the paper. I'm not going to go into details in this. But under these different scenarios, I just calculate how close you get to get the expected conditional distribution, the expected value of X in the conditional distribution. Because this is a very common functional of the conditional distribution. Okay? I'm going to report something here that is some comparison with respect to the reliability score measure that I mentioned before. So here, higher numbers are better. It's just improvement on using that method that doesn't have an entropy term. So looking here on this particular corner, this is just a distribution of scatter plots. This is just a box plot over 80 experiments comparing the fixed neighborhood, we have a neighborhood of 5, I think, method, the tree structure method, and the one that uses the Gaussian approximation with respect to the reliability score method. And there is some, not large, but relatively consistent improvement of using the tree approximation compared to just using the Gaussian approximation. Okay. Yes?
Did you try, so this is sort of an approach where you basically pre-select the questions, right? The active learning sort of approach would be you look at the best observation, then condition on that, do the second observation, and so on. So did you sort of compare the results with active learning situation?
Well, a greedy method would be basically starting from the whole set and then doing the opposite direction. Yeah. So in one sense, I mean, the greedy method is already an iterative procedure. I didn't try to use the greedy method starting from the empty set and going to the whole set. I mean, here, you know in advance how many points you're going to get. Sorry, how many measurements you're going to get. So you can just do the joint optimization together. Okay?
My question was, okay, we can sort of take this offline.
Okay. So here's just a scatter plot showing the error comparing the method without the entropy term against the tree-bound method. And you can see it's very easy to beat a method that doesn't account for an entropy or variability in the choice of set. Because I'm short in time, I'll just say I apply this for that NHS data too, but using, of course, a questionnaire latent variable model structure that wasn't really designed, wasn't really explicit for that study. I just designed my own latent variable model structure by looking at sections of the questionnaire. And then assuming those correspond to different latent variables, and then doing the search there. And again, there is a decreasing error reconstruction by using the tree method compared to the other methods, although the relative gain is quite modest here. Okay? Right, so we have about 10 minutes, I think. So in these 10 minutes, I'm just going to give a general idea on the other side of it. If you do have a pre-specified model, how can you refine it to give a better fit to your data by doing some sort of cheap structural learning over candidates that include your background knowledge as a backbone. So, well, the idea, if you do have some sort of specification on how latent variables should connect to observations, you might want to do a modification of that by embedding this as part of a search space for models that do this relationship between latents and observations. So your search space, you try to define here, for example, ways by which latent variables can connect to themselves or connect to observations. You search among this space to give something that gives a best fit to the data. Okay? There are all sorts of complications here because you evaluate how good the fit of a model is. It's very computationally expensive. Again, because calculating marginal likelihoods is hard. So one approach to that is trying to first modify your search space to be simpler, in a way that makes your problem more tractable, and simplify a way by which you evaluate these models too. So a simpler search space in a simple way of evaluating how good these models are is one essential decision to be done before you can even begin to tackle a problem like that. So one choice of search space here, so I just skipped this, is saying that you do have a pre-specified choice of latent traits that you want to target, and you know which variables are measuring which traits. But there might be all sorts of infinitely many confounding factors that also explain away the associations among observations. So be concerned on how these infinitely many factors might be connected to observations and try to learn this partial structure from data and given background knowledge on this original partition here. Okay, so you're given a partition of how your observations connect to a particular trait and try to patch it up with infinitely many other latent variables. Okay? So it's a much simpler search space if you think in terms of how sparsely connected this might be. So if this is really very sparsely connected, it might be more worthwhile to represent directly what the marginal distribution among these associations is once you marginalize this pool of extra variables that you don't know a priori. So sometimes this is represented by this sparse bidirected structure where I'm saying here, this edge between these two variables means that they have some common parent in this non-specified pool of infinite latent variables. So if your latent traits that were chosen a priori explain away already much of the association, we expect these remaining connections here to be very sparse. So in one sense, this gives you a family of low rank plus sparse connectivity by which you can try to fit the data. Okay? So to make things more concrete, let's again define a parametric form. Again, I'm using multivariate probability models, but I'm going to use some slightly different parameterization for the condition distribution of these observations given the traits of interest. Okay? So instead of doing some standard parameterization, I want to use these models that were designed originally by Jin Huang and Brandon Frey. Jin Huang was actually here at MSR in Seattle, I think. So I defined a CDF, a condition distribution function for the observations given the pre-chosen latent traits. And they define the CDFs in a way that are easy to factorize. So they actually define in terms of a product of small dimensional CDFs. I'm not going to get into detail why you'd learn to do something like this, but you can imagine being able to put together a large dimensional CDF using small dimensional CDFs. And this gives you also an easy way of calculating margins. It's very easy to calculate margins in a model like this. For example, by two-dimensional, three-dimensional margins are very easy to calculate from CDF because you can just plug in the infinite value for all variables you want to marginalize. You automatically get a margin of that CDF. So how is this useful in this context? I'm going to skip this. Well, if you want to see how well the model fit, you need to marginalize your latent variables, and this is very expensive. So instead of using the whole joint likelihood, I'm going to use pieces of the likelihood that have a small size. Okay? So sometimes this is known as marginal composite likelihood. And I can calculate small marginals because of the CDF parameterization gives me automatically a very easy way of calculating marginals. I can put everything together into a composite likelihood score, and then maximizing this score instead of the joint likelihood. So for simplicity, the parameters linking the latents to the observations are treated as points, which I'm estimating by a point estimator. But I'm integrating away the parameters corresponding to those bidirected edges. So there will be a Bayesian penalization for the dependency structure that is due to this infinite pool of latent variables, which I'm not explicitly representing. Okay? Now, the most straightforward algorithm using this composite likelihood is looking at pairs of variables and then looking at the sum of the log probability over all pairs. And then for a given graph structure that tells me which bidirected structures should exist, I have different factors here as a function of that. So G is just my sparse structure that remains after conditioning the latent variables, that main traits. And we have to optimize this in respect to G, in respect to the coefficients linking X to Y, and the covariance matrix of my latent variables, but marginalizing the parameters of the dependent structure of that bidirected set. Okay? So you can do this relatively efficiently, especially if you have a very simple one-parameter representation for the dependent structure. There are these things called copular models, which I'm not going to get into detail. It gives you many families of dependent structures that can be parameterized by a single parameter. So you can actually integrate away some of this using quadrature, for example. Don't need any multi-column method for that. And then here, another nice thing about this is because this is two-dimensional, if you have something like binary data or discrete data, you only need to do one pass through your data because you can cache the bivariate statistics for each pair. So maybe some of you heard about spectral learning methods for latent variable models, for example. The main idea is once you partition a likelihood like this, you can just cache everything that you need with a single pass through your data. And this makes fitting far, far more efficient than doing full maximum likelihood, for example. Okay. There are variations of this, which I don't think I'm going to get into detail, but let me just say that you can also use a EM-like bound here. Do the use of Jensen inequality bound in each term individually. So you can have a different EM condition distribution for each term, okay? And do some sort of EM fitting here. And why would you want to do this instead of doing maximizing likelihood directly is because here in this function you can try to incorporate information from other variables within your pair. So this would be still a one-dimensional integral, this being the dependence parameter, but here being coded in information from some other variables. Of course, the trick is how to do this efficiently. I'm not going to get into detail here, but you can adapt EM ideas within your choice of average distribution and do their bounds separate for each term in a composite likelihood. Okay? So let me just jump to some results. So in terms of how would you apply this, again, my aim here is to give a model that preserves interpretability. So if you are interested in particular latent traits, you want to use this information, the information that these traits are measured in some way by particular measurement model. So I'm just refining this model under these assumptions by adding this extra dependency structure in a way that the model is still interpretable but have a better fit. Okay? So I mean, evaluating this in terms of fitness by looking at the latent embedding of each data point and checking how good these latent features are in some prediction problem. So I fit this to, again, the NHS data with some learning the residual structure given the latent traits that I specified in my first section. And with that, separate some set of questions that are not included in the model. Use the latent embedding, giving a subset of the questions to predict questions outside that set. Comparing the model where I do not do, comparing the model where I do not do any bidirected structure search against the model where I do it. So this is comparing the model that doesn't refine the original latent trait structure against the model that does refinement. So in terms of area under the curve, I'm predicting some binarization of the remaining variables. And here there's much of a change in many of the holdout questions that I have, but in a few cases I get some major improvement. Just showing this is bidirected structure gives you some, this indirect version is bidirected structure gives you some better fit to the joint distribution while preserving interpretability of the original traits that you picked at the beginning of the analysis. Okay? So it's a technique that is aimed not only at predictivity ability, but also interpretability of the model that you obtain in the end. So I can't really make much of this. This is just to show how sparse the structure that I was learning actually is. So these are the blocks corresponding to the partition of a set of 50 variables. So here are all children of the same latent variable. The red points here indicates bidirected edges within the same latent children. And the yellow dots here represent those bidirected edges across children of different latents. So this is just showing that the small rank structure that I have here is combined with a very sparse structure in the remainder. So integrating away those infinitely many variables that might have caused this is probably a good idea because the structure is so sparse, it doesn't make sense to try to add these latent variables explicitly in your model space. Okay? So this is basically it what I look to talk about. And there are, of course, many directions in this work. In terms of trying to compress a questionnaire, there are many things that you could also think of, such as incorporating uncertainty in the model, instead of just using a fixed model. Other criteria that you might want to throw in, of course, calculating the conditional distribution of latent variables is just one criteria. You might have other constraints to deal with. Maybe some of these other constraints can be easily added to the linear program, maybe not. Adaptive questionnaires is something that's not covered here at all. There are some questionnaires where the choice of questions depend on previous answers. So how to deal with a situation like that. For the second half, where you have this idea on patching up a partially specified latent trait model with extra connections, whether there are other sorts of approximations that you can use there in order to make this more scalable. Because even though this requires only one pass to the data, it's still quite an expensive procedure because the iterations that you make to update your model is still quite expensive. So whether there are other ways of improving this is still something that is work in progress. Okay? And of course, experiments are all done in binarizing data. And of course, the original data is not binary. But this extension is relatively simple to ordinal data of a more general type. All right? So this is basically it. Okay? Thank you very much.
So we have time for questions.
Yes?
So what are the take-home messages? If I want to design a questionnaire, what should I do? Suppose that I have a model, or suppose that I don't have a model, but instead I have maybe 100 subjects who answered my questionnaire. What should I do?
Well, first of all, you have to see how useful your latent representation is. So you can do, for example, run this analysis of a subset and see whether the information that you have in a conditional distribution is still representative of what you have with the full set. So you can do, for example, play your different choices of k to see how sensitive your output is on that and see what the redundancy might be. So it's one tool to explore how redundant information is in a questionnaire. Again, everything here assumes that you can reduce your goals to functionals of the distribution of latent variables. I'm not claiming any universality here on how you should design a questionnaires. Only under this point of view, where you're doing smoothing in some latent trait of interest. So this is one tool for doing sensitivity analysis on how redundant your questions are. Another thing is, don't trust your model as being complete just based on the theory on how you are measuring latent traits. There are many spaces of models by which you can search to see what's the best fit to your data. The space I'm designing here is in a way that it tries to preserve as much of the original prior knowledge as possible with some extra residual structured search. So you can see again how much information losing by not using the structure as maybe an indicator that maybe you should just patch it up with a sparse structure, or whether you should actually destroy what you have and try to find a different starting point to begin with. If you cannot really patch it up in a way that the fit is good enough for you, so maybe there's something fundamentally wrong with the original measurement model to begin with. So these are two ways by which you can do this. Again, I'm not saying that you should just take the outputs as a face value, of course not. But I believe this can be used as some sort of sensitivity analysis tools.
So if I have a model which gives me latent variables, and I know what these latent variables are, and I'm designing my questionnaire, why not just ask for those latent things?
Because you can't, right? This is one of the points. If you look, for example, anxiety. Well, what is anxiety? I mean, there are different ways by which you can measure that. So one example that I used once was in test anxiety on students who are preparing to take some exam. So you can ask them how anxious they are with respect to something, but I'm not a psychometrician, I cannot really answer that. There are people here which are much better at this. But there are different ways by which you can try to probe that in different aspects of anxiety too. So you might ask, for example, do you feel heartbeats changing before the exam, or if you're getting sweaty before the exam or something like that? You don't, I mean, even things like democratization, you don't go as an expert whether a country is democratic or not directly, because there are many facets of that. So you can ask, for example, how free the elections of the country are, how free the press of a country is. And then you can use these indirect measures of some sort of trait that would explain away these common facts, these common observations. That's a very good question, but again, there are much better people here qualified to that than myself to answer that.
Any more questions? Okay, let's thank Ricardo again.